Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's get started. Welcome to the second edition of a series that was started by Jean-Raymond Abrial last week. He is here for a month, and he is teaching us about various program refinement methods he has developed over the years, including Event-B and Rodin and such things. So last week we had the first lecture, and we learned about how to refine a bridge system connecting the mainland to an island, and I assume we'll discover other examples today. All right.
Thank you very much, Chad. So we'll continue today with the welcome, everybody. We'll continue today with this example. I hope that we finish it, and then we can start a second example on a mechanical press. And the idea is to cover this next time, and probably the beginning of next week. And then I intend to change completely subject and develop a small sequential program. So next week, and we will see whether we have time to do more. So you remember last time we had an initial model which was very simple, and then we went on to a refinement of it by introducing the bridge, and we did some refinement, and we were stopped with a number of proof obligations for all the events that were already present in the abstraction. The refinement impose a strengthening of the guard and a concrete invariant preservation. And for new events, because we have seen that we have introduced some events that were not present in the abstraction, we have to prove that they refine the implicit skip event. And also the very important thing is the absence of divergence. So those new events cannot take control forever. So we have to define a variant, which would be a natural number, and prove that altogether those new events decrease this variance so that they cannot take control forever, and eventually the old event could be executed also. And finally, for all events, we have to prove relative deadlock freedom. In our case, in this example, this is absolute deadlock freedom because the abstraction was already deadlock free. And so we prove in general that the disjunction of all the abstract guard implies the disjunction of the concrete guards. Okay, so here is the rough statement about the proof obligation. So the guard strengthening first, then the maintenance of the concrete invariant. This is the same for the initialization. And for the new events, we have to define a variant which is a natural number, prove that the variant is decreased, and here is the proof rule for the deadlock freeness. And what you can see is that all these proof obligations are taken care in the tool in the Rodin tool by a plugin called the proof obligation generator, so that we do not have to write down ourselves all these things. So the proof obligation generator study the formal text and generate the proof obligation, and then send the result of what is done to the prover. We will go in the middle of this lecture. We will go on to have a look at the Rodin platform. This is the state of the first refinement. We had a constant d. You remember the maximum number. We have three variables, a, b, c, which are all natural numbers. They are related here with the abstract variable n. So this is the so-called gluing invariant, gluing the concrete variable to the abstract one. Here we have the important invariant explaining that the bridge is one way, A being the number of cars going in one direction, and C the number of cars going in the other direction. So A is 0 or C is 0. So this is the formalization of the fact that the bridge is one way. And then we have this variant. Okay, and these were the various events. Initially, everything is 0. There is no cars nowhere. ML in, so mainland in, when there is no bridge, when there is some car on the bridge going to the mainland, or ML out, C is 0 because the bridge is one way, and A plus B is smaller than D because of the maximum number, and we have then A is increased, and then IL in and IL out. So much for this, and now let's go to the second refinement. So the idea of the second refinement, you remember our refinement strategy, Fund 2, the maximum number of cars, Fund 3, a one-way bridge, and now we are introducing the traffic light, and this corresponds to the requirement equipment 1, 2, 3. So I remind you of the equipment. We have the bridge, and we have the two traffic lights. The problem you see is that if we go onto this, especially ML out here and IL out, these events are supposed to be executed by a driver. So the driver clearly cannot do this count or do this, especially here. So we have to authorize the driver in another way, and especially this is the role of the traffic light. So we introduce a constant set of color and with two color, red and green, that are different. And then we introduce two traffic light, our mainland traffic light and island traffic light. And these two events, IL in and ML in, are not modified. They are not connected to the traffic light. And so now here we have this event, and we would like to handle a refinement for the event ML out. So a green mainland traffic light implies safe access to the bridge. Therefore, we clearly have to introduce this invariant when MLTL is green. So then this is green, then the conditions for accessing the bridge, which were the guards of ML out, are implied by MLTL green. And therefore, this is the abstract ML out we had, and now the concrete ML out is just we replace the guard by MLTL green, and because we have the previous invariant, clearly we are strengthening the guard here because this guard implies this by definition of this invariant. And we have exactly the same thing in the other direction. A green access, a green island traffic light implies safe access to the bridge. So therefore we have this one, and these were the conditions for going out of the island here. And then we have this, which is exactly the similar situation as before for ML out. ILTL green implies this, so we have indeed a guard strengthening. And now we have to introduce new events for turning lights red or green. And again, this is very simple. It becomes green when the condition for being green are hold, and when it is already red, and symmetrically here for ILTL green. So and these are new events, and you remember the new events, we have to prove that they refine skip, which will be easy because this and this MLTL and ILTL didn't exist in the abstraction. But we have to prove, of course, that they preserve the invariant. So here is our situation. We have the two traffic lights and these two invariant. And we have something interesting here as a refinement, which is called superposition refinement. Because you remember last time when we refined, we replaced n by a, b, c, and we had the gluing invariant a plus b plus c equals to n. Now, this is not the case anymore here. Here we superpose, we extend our space by adding MLTL and ILTL, but the variable a, b, c remains the same. So it's called a superposition refinement. And usually these refinements are rather simple. And the summary of the old events so far is just this, and these events are not changed. So this is just what I've explained about superposition. And here is the proof obligation for superposition when we have an abstract event dealing with variable u and v, and a concrete event dealing with variable w and v. So v is the same here and here. What we have to prove, it's called the simulation. We have to prove that under the axioms, under the invariant, under the gluing invariant, gluing the concrete to the abstract variable, under the guards of the abstraction here, then the expression here on the right-hand side of this colon equal are the same under this. So they do exactly the same. There is no change in what is done on the superposed variable. So it's a new proof obligation called sim. So what we have to prove is to apply guard, strengthening, sim, and inv on our four events and with these two main invariants. This is the job we have to do. Remember, the idea is to propose some extension of the state, propose some new invariant. This is what we've done here. Propose some refinement of old events, propose maybe some new events, and then prove that all these diverse propositions are coherent, namely that they obey the proof obligations. So here is the old situation, the new situation. It's quite convenient to put them close to each other because we can see. Sim is completely trivial because we see that the actions here are exactly the same. So there is no problem with sim. And now we have to prove guard. Guard is trivial in these two cases, because in these cases this is the same guard. Precisely, I've already explained this, precisely because of this invariant. This guard implies this one, and this guard implies this one. So far we are safe, it's not too difficult. And then inv applied to these two is all trivially. I have no whiteboard here.
It's behind the...
Oh, here, yeah, here. So you see, we have to prove, for example, ML TL equals green implies A plus B smaller than D, and C equals 0. And so this is a hypothesis. For example, let's work with this one. So we have also the guard, 0 smaller than C. And then we have to prove exactly the same thing. So MLTL equals green implies A plus B smaller than D, because A and B are not changed. And then and C minus 1 equals 0. Okay, this is what I have to prove. So in order to prove this, I can I can do a deduction here, so remove this and put ML TL equals green here, or equals green here. And so now I can do some modus ponens, so I can remove this, and this is what remains here. And here I see that C is 0 and C is positive. So I have a contradiction in the hypothesis. Therefore, I have no problem to prove this. And I have similar, very simple proof for this one and this one and this one and the two here. So these cases are simple. Now we have problem with these two. There is some difficulties, and because in each time when we prove, we stop the proof with something like this. I can show you with a tool. We stop with this. And we discover that we have this and this. We have these two hypotheses which say that both traffic lights are green. Both traffic lights are green is certainly something we want to avoid, because precisely the bridge is one way. And we figure out that we forgot completely this invariant, precisely saying that they cannot be read simultaneously. So let me quickly go to the tool. So we load the Rodin platform. Okay. We have the car example here. We have M2. So we see the variables. We see the invariants. Let's forget about those for the moment. And we have our events. And so now let's go here. And we see that the smiley here is not green. So it means we have some problems. And we can see the problems. This is precisely with ML out and IL out. And there is a fourth one down there. Yeah. So let's have a look at what happens here. So we click twice, and we can see the proof, and we can see exactly what I say to you. We had to prove a contradiction, and we have MLTL green and ILTL green at the point where the prover stops, and this is all. This is the same for all the things. We can have a look at the proof tree. So this is the proof tree. We see the various things that have been done, and we see the point where it stops. So what we're going to do is precisely to enter MLTL red or ILTL red. So let's do this. So in order to do this, we go back here. We go to Edit. We open the invariants. And what I've prepared something. I put true here for this invariant and remove this. So now what I'm going to do is precisely to put this here. Okay, so now I've put this new invariant. So I have a little star here because M2 has been modified. So I have to save it, and look very carefully here. You see the prover will work here. When I do this, and that's it. Okay, so the proof has been done automatically. has been finished automatically, and we have the A here, meaning that the proof was automatic. Okay? Oops. Okay, so we add this, and this is typically of the problem we found. You do a development, you do a proof, you figure out that you cannot do some proof, and you go into the proof that have been unfinished, undischarged, and you look a bit at it, and you figure out more or less easily that an invariant is missing.
So when you prove the invariants, you don't need to prove the new ones. So the other invariants hold because you prove simulation for all the events. Is that the case?
Yeah.
So you don't prove the old invariants again.
No, because what has been proved is already proved. Okay. Now, of course, because I add invariant, now if I change an invariant, then the situation will be different, of course. And then the prover and Rodin figure out which one are concerned, and redo only the ones that are concerned, because we already with this little development have lots of proof. Okay, so let me continue now. Oh yeah, I would say that we could have guessed that this invariant by looking at these two requirements, but this is quite often the case that. People, when doing models, they don't guess immediately what are all the invariants. So again and again, the prover and proving the invariant or proving the refinement helps you debug your model. We figure out also something is that the event ML out, going out of the mainland, has to be now split into two. Either A plus B plus 1 is smaller than D, so we can do that, or A plus 1 plus B is equal to D, so we reach the maximum, and therefore at this moment we have to change the traffic light to red. Okay, so it is possible when you do a refinement that you split an event into 2 or 3 or more. And these two events have to refine their common abstraction. So we have to do this, and we have, yeah.
So how was this figured out during the proof that you need to split ML out?
Here certainly. If you don't have this, and you are in this situation, then you cannot prove that the number of cars is always smaller than or equal to D.
But that's the invariant of penalty equals green, right? And so basically, didn't come out because we didn't make any progress anymore, because we had not enough enable rules, or?
Well, this comes from the fact that we add an invariant concerning the traffic lights. So we add that MLTL is green when precisely or A plus B plus C.
But we didn't have any assignments to the traffic light colors before.
No, precisely. We had. Suppose we go onto this, okay? But we have to prove that these events without the red ones.
Yeah, that's not my question. My question is before you split it, right?
Yeah.
We used the traffic lights and the guards. We had invariants about them, but we never assigned them.
Yes.
What caused us to have to split this? There must have been one proof that failed.
Yeah.
Which one?
Well, precisely the proof that MLTL is green implies A plus B plus C smaller or equal to D.
But I thought you proved them all before.
No, not for this invariant. Not for this. The
disjunctive invariant that one is red.
I didn't prove I didn't prove this invariant for ML out. Okay, and when I want to prove it, I figure out that it was not possible in all cases, because precisely we had to prove that a plus 1 plus b is smaller than or equal to d, so there is a proof by case, and in that case...
yes, of course. And now you see
Okay. Okay, and this is again the intuitive explanation for splitting the event IL out in the same situation. Okay, so we are here now, and we have to prove now, because we have introduced this new invariant, we have to prove that it is preserved. So therefore here, when MLTL becomes green, ILTL becomes red, of course, because otherwise we could not preserve this. And here we have to do the same. Okay.
One more question about that splitting before that. So how you said that you split one event into two, but I guess for that you need to somehow prove that that one of them will immediately trigger the next.
But one of them, sorry?
That one of them would immediately trigger the next, or they cannot be intermediate.
You're not dividing them sequentially. You're saying, okay, these two events together, their guards cover all of the cases.
Yeah, exactly.
It's not like a sequential
okay.
one than the other.
No, it's not sequential.
Just one will trigger sometime.
Okay. Fine. So we have to introduce this. So we are okay with the refinement, and now we have to prove the absence of divergence. So we have to prove that these two, which are the new ones, cannot diverge. And you remember, to prove this, we have to introduce a variant and prove that the variant is decreased. And in fact, we can't. We can't. And precisely these two could take control forever. So if we are in a situation where A and C are both 0, and B is positive, then they can go forever. So this situation is just represented here. We can go forever like this. Okay. So we have a problem here that we figure out because of this necessity of having a variant for the new events that they cannot control forever. So we have to do something. So the situation, there are various possibilities, various solutions here. The solution I choose was to introduce two variables, two Boolean variables, ML pass and IL pass, and say that each light turns to green only when at least one car has passed in the other direction. So therefore they cannot do indefinitely these things. So we introduce here, and what is interesting also, again and again, this is due to the fact that we couldn't prove something. So we figure out that we have this situation. So we introduce ML pass and IL pass, and of course we modify once again, ML out and ML out 1 and 2 with this, because one car has passed, and IL pass the same. And then for MLTL green, we introduce these two things here. And then we can exhibit a variant, which is ML pass plus IL pass. Yeah?
So I understand why you're doing this.
Yeah.
But in practice, this would not be a good solution, obviously, right? Because it means a car would have to wait forever until some other car comes in the other direction, right?
Yeah.
So in practice, actually, there would have to be this infinite loop of traffic lights changing every minute, even if no cars pass, right? In fact, so in practice,
a timer. You want to have a timer.
So in practice, you actually do have this divergence,
yeah.
right? You would want that, actually.
Yeah. This is also a possibility to have a timer.
But it would still be divergent. Yes, because...
it could be,
So would you have to refine the original model if you wanted to allow them?
No, what you could do is to accept that divergence because and this is frequent. Sometimes you cheat. You say not everything is proved for some good reasons, which are not formal.
Weaken the deadlock.
Deadlock.
Is that what you were?
No, it's not the deadlock freeness. It's the variant, decreasing of the variant.
Is it easy to make sure that you're not?
But I think with
allowing what you want to allow, and not
I think with a timer you can still have a variant, because you could introduce a clock.
Right, you have a variant, but corresponding to the original. What you're trying to prove is you're saying the new events are not going to just go on forever without involving some old event, right?
Exactly.
That's still going to be the case in my solution, because I want the lights to change every minute.
Mm.
There's no old event, there's no cars passing, right? So,
Yeah.
So it has to be divergent in a way, but still somehow controlled, right?
Yeah.
So at that point, you would just have to weaken that variant.
Yeah, something like this. Yeah. And for example, in I don't remember which one. Yeah, in another system also, which I think it was different. This was it was about deadlock freeness. So sometimes you have to accept that the system can be deadlock free, can deadlock in a very, very special situation, and then you accept it. And so you don't do you say your proof cannot be done, but you accept it because this situation is very rare, something like this. So here I have to prove a little more. I have to prove the decreasing of the variant, and therefore for doing this I have to introduce this, because here you can see IL pass 1, so IL pass plus 0, ML pass plus 1 here. So here I have to say that when MLTL is red, then ML pass is equal to 1, so I have indeed a decreasing. So again, this invariant is discovered during the proof. So the conclusion of this of the second refinement is that we discover 4 errors. We introduced several additional invariants. We corrected 4 events, and we introduced 2 more variables. Okay. So this is the result of this second refinement. Okay, here are the rules, sim, and that I've added, and here are is the state with the new invariants and the various events. Okay, so let's go now to the third refinement. So in the third refinement, we are going to do something very important. We are going to introduce the sensors to check the entrance or the exit of some cars. But here we are going to be very, very careful on exactly what is the status of our variables. The variables small a, small b, and small c, in fact, so far we were a bit cheating. And that's always the case when one is in an abstraction. Because these variables were the variables as controlled and modified by the future software. And they might be different from the real variable, which is the physical number of cars in the system. So we are going to be very careful and introduce these 2 kind of things, and I will show to you the problem. So here is the physical system, and here is the final system we want to build. We have the controller, which is a piece of software, and we have the environment, and the environment has got physical equipment, the traffic lights, the sensors, and also the physical cars. And here we have some information going from the software to the traffic lights, and here, thanks to the sensors, we have some information coming into the controller. Okay? So what happens here is that when a car is detected here in the environment, this detection is not coming immediately here because it goes through this channel. So in fact, we have a difference between the picture that the controller used in order to control the system and the real system. And in fact, the property that we had, that the number of cars on the island bridge was smaller than a certain quantity, and something like, and the fact that the cars, that the bridge is one way, deal with this variable, with the physical cars, not with these variables. So we have to prove that in spite of the difference between this and this, in spite of the fact that the controller reacts on a fuzzy picture of the reality, the system, in fact, works correctly here at the level of the environment. And this is very, very, very common into an embedded system where your embedded system, your software, it's exactly like we have in our brain. Your software reacts on a fuzzy picture of the environment, and it has to make the environment being correct. So in fact, you see here, I have started my development on this side, and little by little I have introduced the equipment, and I now cover both sides, the environment and the controller. It would have been possible to revert completely and to start here, which in a sense would have been more coherent, to start here and to define exactly at this level on the real physical variables what we want, and then to establish how a controller could make sure that the situation we want is indeed the situation that we effectively have. And so if, a colleague of mine in Zurich has taken again exactly the same that problem, and it has started from here and goes here. And now I think he's right. I think it's better to start here and then to construct, because we want to construct something correctly, to construct something that indeed makes this, the laws that we establish at this point being obeyed. But in this example, I've done the other way around. So let me now see our global system. We have the controller variable ABC and MLPass, ILPass. This is the one we've been using so far. And now we have some physical variable. I put them in uppercase letter. Big A, big B, big C, which are the physical number of cars, which are not exactly the same as A, B, C. And we have precisely to relate them. And then we have the status of the various sensor, which is also some physical variable. And we have some channel variable which correspond to MLTN and ILTL, which is the connection between the computer and the two traffic lights. And here I'm still cheating a bit, because I suppose that the connection between the computer and the traffic light is here, is instantaneous. So that's the reason why I put MLTL and ILTL here as channel variables. So now I have to introduce channel variables in this direction here. And they correspond to the information sent by the sensors to the computer. And here is the way a sensor works. So there is no cars. And then there is a car coming on the sensor. So the car is sitting on the sensor. And then the car is going out to move, to enter the bridge in one or the other direction. And in this edge-triggered, there is an edge-triggered interrupt here that goes to the controller precisely at that moment. Okay? So here is the final situation. We have a controller with ABC, MLPass, ILPass. We have the environment with this. And then we have ILTL, MLTL channels. And then this interrupt channel in the other way. And so you see also something important here. You see that what we are modeling is, we are not modeling only our controller. We are modeling controller and an environment together. Later on, of course, when we finally produce the code, we will be interested in this. And what we are sure is that the code here will be coherent with this. So the system will be correct by construction. We have to be very careful here. Correct by construction relative to the model of the environment we've done. Now, if the model of the environment doesn't correspond to something physical, then of course that software will not be correct. So this is very, very important, and to establish. And here, this is extremely simple, of course. But that environment may have far more things here and and far more assumptions. So what we prove finally is that this final program here, software, will be coherent relative to the assumption about the environment. And moreover, it controls the environment according to some laws which are the basic functions of the system. Okay? So let me introduce now another carrier set, sensor, and two constants, on and off. And then we introduce the four sensor variables. And then we start to figure out some invariants. If the sensor IL in is on, so there is a car on the sensor, then big A is positive, of course. Here big B and here big C. So and this take care of this. The sensors are used to detect the presence of cars entering or leaving the bridge. So we have these three invariants here. They are physical invariant. They are invariant of the environment. And and here, cars are not supposed to pass on red traffic light, only on green one. And you see when ML out 10 is true, which means that the interrupt has been sent to the computer, then it's because the car is moving out of the sensor he was sitting. Then MLTL must be green. So this is here we take into account this rule, and the same for ILTL.
So will the system break down if drivers disobey traffic laws?
I'm not responsible.
That's going to happen, right?
Yeah. Well, if you want to buy if you want this, I can do something, but you have to give me more money. Okay. This is very important, and this is very important if you buy my system that you sign on this. Okay. Because I will not be responsible, and this is also very important to precisely write down all these things. Okay. And it is absolutely fundamental, and it is an assumption about the environment, and my system works if this assumption is obeyed. If it is not, I'm not responsible. Okay.
And the idea is that the sensors are behind the traffic lights, right? So there's a traffic light, you stop your car here, and then when there is green, then you move forward, and then you hit the sensor. That's
No. The idea is that, well, you have the traffic light, you have the sensor, and you are here. Okay?
Yeah, so only after it's green, then you are supposed to touch the sensor.
No. You can sit on the sensor. You can be on the sensor. It's red. You wait, but you remember, nothing is sent to the computer. It's sent only when you leave.
Okay.
Okay?
Yeah.
So it could be in front of it. It could be closer to the traffic light. You don't have to stop on it.
You see, all your questions are very interesting. It means that the purpose of doing this is just precisely to have all these questions coming, okay? And coming only on doing the model. I've not yet written a piece, any line of code, okay? And it's not expensive to do this. But you ask all these questions, we discuss, we disagree, we agree, you pay more or you pay less. This is very important. The problem, and it is always, it is quite often forgotten. This is a problem that we want, suppose our computer is very, 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 very slow. Then it cannot handle, it cannot do the job before a new car is coming. So here I have something which is a bit strange, which is linking some physical and some computer variables together to indicate that, and this was forgotten, the controller must be fast enough so as to be able to treat all the information coming from the environment. And this is often forgotten. And in industry, in developing large systems, quite often people find out this problem that the computer is not powerful enough. And because it is not able to, usually this system work with big loops, and the computer is not able to treat all the information before going to the next loop. And this is what is written here. And now I'm linking the small a and the big A, and you see that sometimes small a and big A are the same. Sometimes we have A is A plus 1, or A is A minus 1, or again, big A is small a. This is precisely here this question that we have a fuzzy picture, A, which is not always the same as big A. And we have the same for B and C. And now what we have to prove is precisely that the one way and the fact that the number of physical cars is smaller than D is still true. So here we prove that, again, in spite of the fuzzy picture on small a, small b, and small c, the program is able to maintain this one. So if we start the other way around, we would have started with this and prove that we have a similar law inside the computer. So you see, again and again, this is very important for this kind of system, and very often forgotten to make the distinction, and I want to hammer this, between the physical variable on the environment and the logical variable inside the computer, and showing that they are not exactly the same, but in spite of that, the system reacts correctly. Yeah.
Are there any provisions, say, in Event-B or whatever, for separating the two? So, for example, having events that are only supposed to happen within the software and only environmental. So you actually prove that the software isn't secretly looking at the physical variables in the model.
Yeah, exactly. And this is precisely, this is very important what you say here. The problem is that when you are in an abstract, at an abstract level, you can cheat. So the environment can look inside the computer, and the computer can look inside the environment without going through the channels. Because the idea is to always introduce a channel at the very end. Okay. So for a while, you have a hybrid system, which is a monster, which doesn't exist. Okay. And then you refine, and this is the reason why I've chosen to have small letters and big letters to precisely make the distinction between the two. And then you have to figure out that all the events that are supposed to be in the environment are working only with big variables, and all the events are dealing with the computer, with the future software, are with small variables. And of course, in the invariant, you might have mixed things. Okay. And then you separate things, and it's possible to, there is a plugin in Event-B where you can decompose, so you decompose, and you have exactly the system that I showed to you. You have the environment, the software, and you have channels between the two. Yeah. And now I'm not going to go onto this, so we have some refinement of these events. And here is the final situation. We have, and that's very interesting. We have as many physical events as we have logical events in the computer. So this is the environment, and this is the future software.
So the separation between physical events and logical events makes a lot of sense. But at some point, you have to model that the physical event causes some logical variable to change in the channel.
Yeah.
So is that special? Because that seems to be one case where you do have a cross, where you involve both physical and logical variables, right?
No. You have three kind of variables. You have the logical variable, you have the physical variable, and you have the channel variables. Okay, and so the channels variable for channel going out are written here and tested here, and the other way around here. So you have really these three kind of variables.
But does the tool impose those three?
No, the tool doesn't impose anything here. The tool doesn't impose. This is a way of doing it systematically. So question on proving. So we what is to be systematically proved: invariant preservation, correct refinement, no divergence, and no deadlock. Where are these proofs done? So I've said many times the proof obligation generator, and then the prover, which is automatic or interactive. And the main tools are the proof obligation generator, the prover, and translator into hardware or software languages. And the tool is embedded in a development database.
What prover do you use in Rodin?
Sorry?
What prover do you use?
We develop our own provers. And we have also connections to external prover, but so far this is mainly our own prover.
What kind of a prover is it?
It's a prover working with set theory and arithmetic. And we have one prover working directly at this level. And we have also another prover and two other provers called PP and UPP. So there is a translation of the set theoretic statement into first order predicate calculus. And then this is a first order predicate calculus prover that does the job.
Okay. And also your own first order prover?
Sorry?
So your own developed?
Yeah. So let me just show you the final thing about it. So if I go on top here, and on this, on this little window here, I have the statistics of the proofs. So you see, the number of proofs is quite significant, 252 proofs. There are lots of proof at this level, and we have two interactive proof, little interactive proof, and they are essentially on the deadlock freeness, because deadlock freeness, there are lots of disjunction, and the prover could be better on this. But this is not too bad. But it shows, you see, that a simple system like this requires a lot of proof to do all the things. So it's exactly 2:30, so we are going to stop here now. So next time I will again start the mechanical press. And here, what I'm going to introduce is the notion of formal design pattern. You know the notion of design pattern in OO. You know that. And the idea is to borrow this concept and to see whether we could have something that is occurring very often, so that off the shelf we have little things that are prepared, and we can use them within some formal development. Okay, thank you very much.